Welcome to the lesson in sections 4.4, not 4.4. Make that 11.4, everyone's favorite from the lesson we had on this in class on the word problems. So I took a different approach when I did this the second time around and found that it was significantly easier when doing so. Instead of solving for r in the problem, I went about the approach and solved for time, and this produced quadratic equations that were a lot easier to solve. So we're going to go ahead and do the 4 problems as promised, as well as tackling some of the additional problems in section 4.4 that will be addressed in a different video for this section, where we'll have to isolate some variables. And that's a bit of tedious work, but not as difficult as the 4 problems we're going to tackle here. Taking a look first at question 2. So you had question 2 copied in your notes from class yesterday, and if you weren't in class, please look either online or in your textbook at page 801, problem number 2. So this is going to be section 11.4, page 801, problem number 2. So remember that you have, if you have the electronic copy of, or if you have MyMathLab, then you can look up the actual textbook problems, because I don't want to write those here. So what the question reads is as follows. During the first part of a canoe trip, Terrell covered 60 kilometers at a certain speed. He then traveled 24 kilometers at a speed that was 4 kilometers per hour slower. If the total time for the trip was 8 hours, what was the speed on each part of the trip? So as we did in class yesterday, and as you'll find in the textbook too, we're going to go ahead and we're going to make a dirt table, as it is often known. Remember that we have the formulas for this, so we're going to have the following formulas, which you probably have in class from the class 2, where distance is equal to rate times time. So this is one type of formula. If I take distance equals rate times time, and I divide both sides by t, this allows me to reduce t here, and that's going to give me r is equal to d over t. So this here is the second formula. So r will equal d over t. If I take the same formula, and this time I divide by r instead, I'm now going to have the formula t is equal to the distance over r. And in this formula, let's define what these variables are. D is equal to distance. R is equal to the rate, or speed, or velocity, whatever you want to call it. And t is going to be in time. The units of each of these may change. Distance can be in miles, it could be in kilometers, it could be in feet, whatever unit you're working with. Time could be in seconds, it could be in minutes, it could be in hours. And the rate will be the units of distance divided by the unit of time. As we have here, you'll see that for r, it's the units of the distance divided by the unit of time. We'll see that as we work with different problems here. So let's go ahead and continue with problem 2 and make our dirt chart, D, R, and T. It discusses during the first part of a canoe trip going 60 miles, going at a certain rate, and going at a certain time. The second part of the trip is going to be 24, not miles, but kilometers. So the first part is going to be 60 kilometers. The second part is going to be 24 kilometers. It says that in the second part of the trip that this is 4 hours slower. And as we discussed in class yesterday, if this is 10, this is going to be 6, 4 kilometers per hour slower. If this is 20, this is going to be 16. If this is going to be 50, this will be 46. So what do? I would take 10 minus 4 to get 6. I would take 20 minus 4 to get 16. I would take 50 minus 4 to get 46. So I'm going to take r minus 4 to get the rate of speed into here. Now the time here is the one that's a little confusing for some people, because they don't tell us if it's so much time less or so much time more. We would of course expect that because the rate is slower, well, maybe not, because the distance is significantly shorter, so can't be quite sure what's going to happen with the time. But we do know that the total time for both parts of the trip is 8 hours. So if this is 5, this would be 8 minus 5, or 3. If this is 2, this would be 8 minus 2, which is 6. If this is 1, this would be 8 minus 1, which is 7. So if this is t, then this is going to be 8 minus t. And that's how we write the algebraic expression for the amount of time that it goes to take on the second part of the trip. So this is the first part of the trip, and this is going to be the second part of the trip. So what we're going to do now is we're going to take the information that's in these dirt charts for the first part of the trip and the second part of the trip, and we're going to go ahead and we're going to put these, and we're going to try to solve for, in this case, we'll go ahead and try to solve this in terms of R. So what we're going to do is we're going to plug this information into, let's see, we're solving for the rate, so solve for, let's see, let's go to one of these two formulas here. And which one do we want to use? I think we're going to go ahead and let's go ahead and use this one here. So we have d over time equals r. And watch what happens when we do this. So the first class saw me solve it for t yesterday. We're going to go ahead and solve this one for r. And let's see what happens. So if I use the formula r equals distance divided by time, well, I'm going to label this number 1. I'm going to label this number 2. So for number 1, what's my rate? It's simply r. What's my distance? It's 60. And then what's my time? It's simply t. Now, for number 2, the second one, my r is not r, it's actually r minus 4. So I'm following this formula. What's the distance we go? This time is 24. What's my time? It's 8 minus t. Well, this one is good because I have all this set equal to r. Here, I need to get r by itself. In order to do that, I'm going to go ahead and add 4 to both sides. That's going to produce for me r is equal to 24 minus, or divided by, 8 minus t plus 4. So in the first part of this problem, I have to find the variables for the two parts of the problem. In the next one, I use one of the two formulas that I derived. We'll label this one number 3 over here, to try to get r equal to the first part of the problem and then r equal to the second part of the problem. In the same problem, the r's are going to be equal, so I'm going to set these two equal to each other. And I'm going to go ahead and do that down below here. So this is going to give me, let me move this up a little bit now. This is going to give me 60 over t equals 24 over 8 minus t plus 4. Now, in this part of the problem, we can see we have an awful lot of fractions going on here. And gosh, wouldn't it be nice to simplify those fractions, eh? So what do we have to do? We have to take a look what we have for common denominator, or least common denominator. Well, here we have t, and here we have 8 minus t. So I'm going to multiply everything by t times 8 minus t. When I multiply the first part through, the t's are going to reduce. Because the t's will cancel in this first part of the multiplication, all I'm going to do is multiply 60 times 8 minus t. So the first part is going to give me the calculation 60 times 8 minus t. And the second part of the calculation, and this is going to be equal, so let me put that equal sign in there. I now have t times 8 minus t times the quantity, let me put that through here, of 24 over 8 minus t. Once you can kind of isolate this, and you can do this with your fingers, you'll see that the 8 minus t's should reduce each other, leaving you with only the 24 times the t. So that's going to leave us now with 24t. And then over here, when we multiply t times 8 minus t times a positive 4, we see that there's nothing in the denominator to cancel the t or the 8 minus t. So I'm going to go ahead and write this part as plus 4 times, and let me bracket this, t times 8 minus t. The one part of this problem I'm going to change before I bring this problem up here to continue to work on it is I'm going to change this to 4 times. I'm going to distribute on the inside now. So t times 8 minus t, that's going to give us 8t, and then t times negative t will be minus t squared. So now I've got 60 times 8 minus t equals 24t plus 4 times 8t minus t squared. What we're going to bring up here now is going to be the distributed version of this. So going down here, 60 times 8, 480. 60 times negative t, negative 60t. That will equal 24t. Now let's distribute this. 4 times 8 will be plus 32t. And then 4 times negative t squared will be minus 4t squared. So what did I do between here and here? I distributed. So this is all math that we've learned earlier. It's just a lot of it's converging into a single problem. So hopefully you'll have a chance to watch this a few times, maybe more than a few times, and get the gist of this so you feel more comfortable with tackling all of these mathematical computations in one problem. After we distribute now, we need to combine like terms. And we do that on each side of the equation, not across it, just on each side. Here, there's nothing to combine. Over here, we have 24 plus 32, so that's going to produce for us 56t minus 4t squared, and that's going to equal 480 minus 60t. So what I'm going to do now is, since I know this is a quadratic equation, I'm going to go ahead and get this negative 4t squared to the opposite side, so I can write it as positive 4t squared. So we're going to add 4t squared to both sides. Now you don't necessarily have to put it under nothing, but there's nothing to combine it with, so I just put it at the end here. And then I'm going to subtract 56t from here, and then subtract 56t from here. This will reduce, leaving me with 0. And that's what I want. When I need to solve a quadratic equation, I need to get that quadratic equation set equal to 0. So I'm going to do one thing here. I'm going to write down 4t squared. This 480 is positive. I know that because there's no sign next to it. So I'm going to just go ahead and put that here, because I'm going to try to write this like in 4t plus or minus something t, 4t squared plus or minus something t plus the number. So I have this in at squared plus bt plus c equals 0 form. And when I take negative 60t and minus 56t, that should give me negative 116t. So now I have the quadratic equation, 4t squared minus 116t plus 480 is equal to 0. Those students who were in the first class who saw me do this differently will notice that this may be a little easier to solve than the equation that we were up against yesterday. We want to simplify this a little more if we can to make it a little easier to factor, especially since the a coefficient is not equal to 1. So we can in fact factor 4 out of that. So when we do so, that's going to give us t squared minus 29t plus 120, and that's going to equal 0. Now, once we factor 4 out of this, we do in fact have to divide both sides by 4 so that we get the equation t squared minus 29t plus 120 is equal to 0. Now, some of you who may not be really strong in factoring may have to use a quadratic formula to try to simplify this. Still doesn't make it an easy problem. There's still some number crunching. But if you can't think of the factors that will generate this, use a quadratic formula that you should know how to do. But for the factors of this, I'm looking for two numbers that multiply to 120 and add to negative 29. Well, that's going to be t minus 24 and then t minus 5. Because 24 times 5 will give 120. A negative times negative is positive. And negative 24 plus negative 5 will be negative 29. So here are our factors. Always got to set this equal to 0 now. So I'm going to take each factor now, set it equal to 0. And from this point, I should know that t is equal to 24 and that t is equal to 5. Once you get your solutions to your quadratic equation, now you got to see, are both applicable or is only one applicable? And usually only one is going to work. Much like the radical equations that we solved in the work we did in chapter 10, where we had to test both. Sometimes both would work, sometimes only one would work. Well, here, typically, only one of them is going to work because it's a real-world problem. So if we look, for example, here at time being 24 hours, if we were to put that value of 24 into 8 minus t, well, that's going to give us a result of negative 16, and that just does not work. So we're going to go ahead and put a line through that, so we remove that from consideration. And we want to see, does this solution make sense? So we're going to go ahead and put 5 in for time here, because remember that 5 is the value we have for t, but the question is asking us for the rate. Okay, so, and the rate specific on each part of the trip. So we have the formula now, d equals rt. Well, if 60 equals r times 5, because that's the value of t we found, we divide by 5, and then r is going to equal 12. So we have that here for this part of the trip. Now, according to the table, we should generate the values. Let's see, if r is 12, 12 minus 4 should give us 8. And according to this part of the table, we could see that if t is 5, then 8 minus 5, that should give us a value of 3. And if we know that distance equals rate times time, 24 should be equal to 8 times 3, and in fact, it is. So now we know that our calculations have obtained something that makes sense not only in the solution we got from the quadratic equation, but makes complete sense with the values that we obtained in the original table that we used. So to come up with a final answer to this question, we'll just call that first rate, rate 1, and that second one, rate 2. So let's call this R1 and this R2. So the first rate on the first part of the trip, that's going to be 12, and this is going to be kilometers per hour. And then the second part of the trip, the rate is going to be 8 kilometers per hour. And you need to make the slashing. You need to indicate the units that reflect the rate. In the question, as you'll read, he talks about this in kilometers per hour, and this is how you need to write your answer in its final form. That is our solution to the first of the 4 problems. The next 3 I'm going to go through, I will go through with a little less development and go right more to the solution for these so that you get a better flow of how these are solved. Let's go ahead and go now to question 4. Let me make sure that this is properly centered in the camera now. So we're going now to question 4, and question 4 reads as follows. Mallory's Mazda travels 280 miles, averaging a certain speed. If the car had gone 5 miles per hour faster, the trip would have taken 1 hour less. Find Mallory's average speed. So in this one here, we're going to make our dirt formula or dirt table again. So we're going to have 3 columns like this, 3 like this, or 3 rows and 3 columns. So it's D, R, T. This is the actual trip, and this is the faster trip that they're talking about. So I'm just going to label it as such. So we know that both trips would have been the same distance. Whether he goes faster or slower, if the trip is the trip, it's going to be 280 miles. For the rate, all we know is that the trip he did was at a certain rate at a certain time. The question contends if he had driven 5 miles per hour faster, then the trip would have taken 1 hour less. So let's just focus on that 5 miles an hour faster. Suppose he had gone 20 miles an hour. If he had gone 5 miles an hour faster, he would have gone 25. If he had gone 50 miles per hour, he'd have gone 55. So if he goes R miles per hour, he goes R plus 5. So that's how we get this here. So let's say, for example, now let's focus on the time. Let's say he took 10 hours. Well, if he took 10 hours here and he took 1 hour less by going faster, instead of 10 hours, he'd be 9 hours. If he had taken 20 hours, he'd have gone 19 hours because he would go 1 hour less here. But if he goes t hours, then he's going to go t minus 1 hours. So you will recall that I did kind of play this out in class yesterday, and please let me know if you want to see how this is done again. I can certainly elaborate on this in greater detail when I'm in class. I could do it here too, but it's easier to actually kind of show in person to enable you to ask clarifying questions. So for this one again, we're going to go ahead and we're going to solve for r. So we're going to use the formula r equals d over t. So we've got the original trip and then we've got the faster trip. So for the original trip using r equals d over t, we're going to have r from here equals 280 over t. For the faster trip, we're going to have r plus 5 equals the same distance, 280, divided by the time, which in this case is t minus 1. Now, that's not all we need to do yet. We have this as r, and that's fine, but this is r plus 5. I need to get the plus 5 to the opposite side. So I'm going to subtract 5 from both sides and write this as r is equal to 280 divided by t minus 1, whoops, not plus, but minus 5. So this is a minus 5, guys, not plus. That's a minus 5. At this point now, I'm going to go ahead and I'm going to set both of these parts equal to each other. Since they both equal r, I can set them equal to each other. So I'm going to write this now as 280 over t is equal to 280 over t minus 1 minus 5. And let's go ahead and see how we can continue to solve this. So I want to clear the fractions out of this, and I see I have the denominator of t here. I have the denominator t minus 1. So I'm going to multiply this by t times t minus 1. Now, one thing that may be helpful, and you can kind of write this above yourself, in the case, for example, like when we're going to multiply this by negative 5, and nothing is going to reduce. Well, let's just go ahead and kind of write what the product of this is together up here. So we'll refer to that in a moment. T times t will be t squared. T times negative 1 will be negative t. So I'll show when we use that in just a moment here. So when we multiply just these two items here, we should notice that these two t's are going to cancel, leaving us with 280 times t minus 1. So this is going to be 280 times t minus 1 equals, here when we multiply these two things together, we should notice that the t minus 1's reduce, leaving us with 280 times t. This is going to be 280 times t. So I'll just write this as 280t. Now, when I have minus 5, I notice, let me just put that there, that when I multiply t times t minus 1, nothing reduces. So instead of putting t times t minus 1 here, I'm going to go ahead and just put the product of this, which is t squared minus t. Now, if you don't like this particular step and don't understand how I did this, just do the work I showed in the first problem, kind of distributing it through. But I think this will probably save a little time and maybe reduce some of the confusion. Okay, so let's go ahead and distribute where we can. So I'm going to distribute through here, and I'm going to distribute a negative 5 through here. So this is going to be 280 t minus 280 equals 280 t. Now this is going to be negative 5 times t squared will be negative 5t squared. Negative 5 times negative t will be plus 5t. So one little thing I'm going to do in this problem, so you may want to kind of wind the video back a little bit and kind of stop this. I see I have the exact quantity on both sides here. So I have a 280t here, I have a 280t here. I could combine like terms here, But when I get this rare kind of a gift, I just go ahead and cross this out, because if I take 280 away from both sides, it's going to disappear. And I'm just going to go ahead and write this as negative 280 equals negative 5t squared plus 5t. So this simplifies the problem a great deal. I know this is quadratic because I have a negative 5t squared term. The important thing is that we have t squared. So what I'm going to go ahead and do is I want this to be positive. So I'm going to go ahead and add 5t squared to both sides, and then subtract 5t from both sides. I'm going to add 5t squared to both sides, and then I'm going to subtract 5t from both sides. Notice I kind of put this here to try to keep everything even, so I'm going to just move that up a little bit so you can see that. And then what we'll have here is going to be 0. And this will give me 5t squared minus 5t minus 280 is equal to 0. So that's the quadratic equation I get for this, which I'm going to begin to simplify here. And I'm going to try to make sure that everything is in the image of the camera and continue on with this. So now I'm going to go ahead and bring this original equation, or original quadratic equation up here. So now what I'm going to do is I'm going to go ahead and factor 5 out. That's going to give me t squared minus t. Now, let's see, my quick math here is going to be 20, 40. That's going to be 56, I believe, if I'm not mistaken. So minus 56 equals 0. I'll divide by 5. That's going to make it t squared minus t minus 56 is equal to 0. And now, with some quick handy-dandy factoring, I'm going to go ahead and come up with the factors of t minus 8 times t plus 7. Because negative 8 times positive 7 will be negative 56. Negative 8 plus 7 equals negative 1. That's exactly what we're looking for. I set each of these factors equal to 0. Again, you can use the quadratic formula for this if you want. There's no method of solving a quadratic equation that is required here. So you can choose whatever method you want. I'm just going with the factoring because I think it's the most straightforward. So I'm going to add 8 to both sides. I didn't show this part of the work last time, so if you need to see that, that's fine. I'm going to go ahead and do it. So we have 2 times now. We have t equals positive 8 and t equals negative 7. Well, obviously, a time of negative 7 doesn't make sense for this, so we're going to go ahead with t equals 8, and we're going to kind of see if this makes sense in relation to the problem. So if we have t equals 8 here, then t minus 1 should be a time of 7. And we're going to see if that makes sense in relation to the problem. So we have the formula r equals 280 over t. So let's go ahead and kind of use that. So we have r equals 280 over t. So for a time of 8, if I take 280 and I divide by 8, r is going to give me 35. So if this is 35, r plus 5 should be 40. So let's go ahead and just check that and see if that makes sense. We're going to try this one down here where we have 280 for the distance and 7 hours for the time. So we have here r equals 280 divided by 7, and here r equals 40. So if r is equal to 35, r plus 5 equals 40, then it looks like we've got the correct answer to this. However, make sure to look what the question is asking. It asks to find Mallory's average speed. It's in the first problem that we're going to find his average speed. And in speed, we're talking miles per hour. So his original speed that he goes, not the faster speed if he had driven faster, but his original speed is 35, and mph is the standard way to express miles per hour. You have to make sure when you write the answer to this that you give the limits to that question as, or the measurements as well, in terms of how we write the rate of speed. So the final answer to question number 4 is 35 miles per hour. Given the time of this video, we're going to go ahead to do video part 2 to show the questions 6 and 8 coming soon.